So let's start something new, parametric equations. Now, we've worked with equations for a long time, but most of the time our equations are in terms of x and y. X being our horizontal piece and y being our vertical piece. Horizontals and verticals give us a nice friendly shape called a rectangle. So we've done a lot with rectangular equations. Say, for example, y equals negative x squared over 72 plus x. So that's a quadratic. We've done plenty with quadratics before. But that's just using two variables. Sometimes it's going to be more practical to do more than two variables. Oftentimes, if we bring in a third variable, we can either simplify or make it more applicable to a certain situation. So, let's say we brought in a third variable of t. So let's say we let x equal 2t. Correspondingly, if x equals 2t, and we want to redefine y in terms of t, we would just substitute in for x with 2t. So 2t squared is 4t squared. 4 over 72 is 18. So it's negative t squared over 18 plus 2t. So this says the same thing as that. But really, we didn't make it much more simple. It's pretty much just as difficult, just as challenging. But ways that we could make it easier is if we wanted to, say, get rid of that fraction. So a way to do that is make x equal to 12t. So then when we substitute 12t in, 12 squared is 144. 144 over 72 is 2, so it's negative 2t squared plus 12t. So we were able to make this into an equation where there's no more fractions, simplifying it, making it a little easier to work with. So we've defined the same function in terms of two equations to make it a little bit more straightforward. So that's a way to simplify using a parameter, using a third variable. But oftentimes we're not just trying to simplify it, we're trying to make it more applicable. So you're not going to see where this is coming from until we get to the end, but let's say that x equaled 24 root 2 times t. So if x equals 24 root 2 times t, so 24 squared is 576 times 2 is 1,152, and 1,152 divided by 72 is actually negative 16. So negative 16t squared plus 24 root 2 t. Now, last video we talked about something called gravity, and I hope you guys were familiar with it. But gravity in terms of feet per second squared is negative 32 feet per second squared. That's half of that. If you think back to physics with projectile motion, the height of an object thrown was y of t equals 1/2 times gravity times the time squared plus the initial velocity times the sine of the angle it's thrown at plus your initial height. And horizontally, it was the initial velocity times the cosine of the angle it was thrown at plus your initial horizontal position. So 1/2 times negative 32 gives us that. So this is the velocity times the angle it's thrown at, the velocity times the angle it's thrown at. And that's 48 times root 2 over 2. Sine of 45 is root 2 over 2 degrees. And this is 48 times root 2 over 2. So this equation can be broken down into two parametric equations that show that it's really the path of an object thrown at 48 feet per second at an angle of 45 degrees. That is a large part of what parametric equations are going to be used for. But we're going to start with just the basics of it. So any rectangular equation, there's an infinite number of ways to break it down into a parametric equation. And you could just choose, just like we did here. I really just chose 2t. I chose 12t. You can choose parameters to make it easier. Now, sometimes you're going to be given your parameters, and you're going to need to, or you're given your parametric equations rather, and you're trying to get the curve that it models with those parametric equations. So you're going to have two equations, each in terms of the same variable, that will produce your x and your y, and that will tell you your horizontal locations. So this is oftentimes when you have two things being affected by time. Most of the time our parameter is going to be time. Not every time, but most of the time. And these parametric equations together will produce what's called a plane curve. So what a plane curve is if you have two functions, f and g, and they're continuous functions, and they are in terms of t, and oftentimes we're going to be restricted to a set interval. Not all the time. If the interval is not given, you will just be taking whatever the domains are, the intersection of the domains of f and g, if the interval is not given. But oftentimes it will be given. So if you have two functions in terms of t over an interval, then the set of all order pairs f of t, comma g of t will form our plane curve. Oops, not the cure, plane curve. So I'm just going to call the plane curve C. And in C, our x parameter is f of t, our y is g of t, and these are our parametric equations. With parameter t. So that's what a plane curve is. And plane curves do not need to be functions, but they do need to be continuous. Actually, they don't need to be continuous either, I'm sorry. But they usually are. So let's try a couple examples. Just some straightforward ones for now. Next week we'll get into more complicated ones. But let's say we had x of t equals t squared minus 4, and y of t equals 1/2 t. And let's say our interval is t between -2 and 3. Now, it's not as easy to determine what type of function it's going to be from this. It's not always easy. This time it's pretty straightforward. To start out with, it's going to be pretty straightforward. We have a linear expression and a quadratic. If we plugged a square into a first power, it stays square. If we plug a first power into a square, it becomes square. So regardless which way you substitute, which way you compose these, you would end up with a quadratic. So this is going to be a parabola, but it's a restricted parabola. So we don't know what section of the parabola it's going to be. And we don't know whether it's opening up, down, left, or right. So what we can do is we can make a table of values. So we can have, oops, I bumped it, t, x, and y. And if we're going from -2 to 3, -2, -1, 0, 1, 2, 3. Oh, I wanted those here. -2, -1, 0, 1, 2, 3. Because t is our input. So we don't care about that up top. Sorry. So -2 squared is 4, minus 4 is 0. Hey, 2 squared is 4, minus 4 would be 0. And then -1 squared is 1, minus 4 is -3. Oh, 1 squared minus 4 is -3. And 0 squared minus 4 is -4. And 3 squared is 9, minus 4 is 5. And then for the y, we have half of each. So -1, -1/2, 0, 1/2, 1, 3/2. So these give us the actual points. That's our x and y. So we can take that and we can actually plot it. Oops. So I'm going to make my axes. On the x-axis, our x values were 0, -3, -4, -3, 0, and 5. So a scale of 1 will be practical. So 1, 2, 3, 4, 5. That's our highest value. And then 1, 2, 3, 4, -4. That's our lowest value. And then for the y's, it was -1, -1/2, 0, 1/2, 1, and 3/2. So I'm just going to do a scale of 1/2. So 3/2 is the highest. -1 is the lowest. So now we can plot our points. So we had 0, -1, 0, -1, -3, -1/2, -3, -1/2, -4, 0, -4, 0, -3, 1/2, 0, 1, and 5 3/2. So we started here. That was our next one, and then we continued through like that. So that's our parabola, but because of the restrictions, these are the pieces we're left with. That's the part of the parabola that we have. So that's just the basics of parametric functions. Next week, we'll go a little further in depth and talk about some more applications. All right, have fun.